like this, right? And so in linear logic, we have two sorts of multiplicative of conjunction. So if you have, like, let's say A, B, and C, this is one form of conjunction, which is a tensor. Here, it will not copy A and B to the premises. So the premise have C and D, but it can choose. So either both A and B can go here, and this will be alone, or B can go here and all the other possible combinations. Whereas if you have additive conjunction, A and B will be copied. So this is the basic system.
My specific doubt was, in some places you had written gamma, comma, phi.
Right.
Was it saying that either all of the formulas in gamma are true or phi is true? Or was it like gamma, v dash phi?
Derives gamma.
Yeah, so it's like in the presence of phi, in the presence of gamma, we are working with phi, that sort of thing. Everything's on the way.
see.
Yeah. Right. So as if we are doing this for the first time, we have systems for proof systems for mu-mal. And we have the co-induction principle, which says that if alpha is a prefix point, then alpha is below the greatest fixed point. You can think of this as an inference rule like this, where you can think of psi as basically alpha. And this is a deep problem in logic in general, is that induction and co-induction does not bode well with cuts. And as proof theorists, our only goal in life, well, not only, but one of our major goals in life is to eliminate cuts. And this is something which is not possible here. And if you have seen cut elimination in piano arithmetic, one way of doing it is by having an omega rule, which looks something like this. So you replace the generalization rule of second order arithmetic and just say that if something is true for all n, it basically means that it is true for 0, it's true for 1, and so on. And analogously, in mu-mal, if basically you're saying that phi is true for top and phi is, so basically computing the fixed point iteration forever to get like from, instead of doing it from the bottom, you're doing it from the top, right? So because you're computing the greatest fixed point, so you have this big set of everything which is possible, and then you're constraining it so that you get the greatest fixed point. And this is what this rule tells you. But using an omega rule is very early 20th century logic. Can we do something different? In particular, can we learn something from the success of automata theory in the later half of the 20th century? And yes, we can. So we allow proof trees to be infinitely deep, and we see the least and greatest fixed points as sort of odd and even parity. And now we are in the world of Rabin, and we are in the world of Street, and so on. So we have the same rules for mu's and nu's. It's just unfolding. But we say that we accept a proof tree if it is progressing. And the proof trees are infinite, by the way, now. So these are infinite trees, but finitely branching. And for every infinite branch, there's a thread satisfying the parity condition. So we would like to hit these sort of very strong results of Rabin. So the parity. Right. So thread is basically this. You just follow a formula along a branch. If some rule is being applied, you follow its subformulas. If it's not being applied, you just follow itself. So this is a thread. This is a thread. Here there are two threads. One is you follow the news, and one is follow this formula along its subformulas. So the parity condition says that the minimum formula repeating infinitely often is of even parity. And this is just like a parity automaton or a parity game. So Now we would like to say which of these proofs are progressing and non-progressing. This one is not, because the minimum formula, well, the only formula repeating infinitely often does not even have a new, and only news have even parity. So this one doesn't work. What about this one? Oh, okay, I already gave the answer. So in this one, new does occur infinitely often, right? So it follows like this. So mu, new, mu, new. You have the same formula here. So basically you keep doing like this, but it is not the smallest formula occurring infinitely often. And so the smallest formula infinitely occurring is odd. In this case, you still have this formula. So this thread won't contribute to the progress, but you have this simple new XX, which is a formula which occurs infinitely often and is of even parity. And this gives you the progress. So this is progressing. At least one thread along every branch. So it's a alternation of quantifiers. For all branches, there exists a thread. Right. So in conclusion, we have two systems, right? So we have the omega system where you have the omega rule. Everything else is the same in these two systems. These are well-founded trees, but potentially infinitely branching. Yeah. On the other hand, we have the opposite situation. We have the same rules for mal and for the least fixed point, but we have this unfolding rule for the greatest fixed point. And in this case, we have infinitely deep trees or non-well-founded trees, but they're finitely branching. And you can imagine like doing sort of combinatorics on this. If you can say, oh, I want to restrict a condition that the trees are regular, and now you are in business, right? So our question was proof theoretic, that do they prove the same theorems? And surprisingly to us, we realized that they don't. We saw that the set of theorems proved by non-well-founded proofs is strictly smaller than the set of theorems proved by omega rules. So this will be the rest of the talk. I'll basically prove this theorem. It's divided into two parts. First, I'll show the inclusion, and then I'll show the non-inclusion. So, okay, this wasn't supposed to happen. All the spoilers. I wanted to milk that. Right.
Induction versus omega rule. Do you recall?
In terms of the theorems that they can prove, omegas can prove a lot more. I mean, they can...
So the question is, why is this a surprise? Because if you think about the
right, but
rule as induction and this as the
no,
omega
but that's a comparison with induction and omegas. But if you compare induction and non-well-founded in piano arithmetic, they are the same. And here I'm comparing, omega and we are comparing omega and non-well-founded here. And that is the same in piano arithmetic. Here, that is different. Right. So basically, we need to show something like if there is if mu mal the non-well-founded proof system proves a formula phi, then the well-founded system proves a formula phi. Just fix phi. And a proof P of phi will define a well-founded proof. Well, we'll define a proof by co-induction on P. And so basically the point is do everything which the same, just when you come to a greatest fixed point, do a different rule. But the problem is that you cannot immediately fire the co-induction hypothesis because the formulas are different, right? So we have to go to a notion of projection, which I'm defining by induction on, by induction on N, and a proof of this object, of this sequent, so that I can plug it here, right? And I'm using this proof which was given to me to build this projection. So P0 is just top. So that's just true. We end the proof there. We have truth. And Pn plus 1, you'll have phi of n plus 1 of top. But that is, so a proof of Pn is basically phi of phi n plus 1 of top. But then what is, how do you define the sequent? It's just replacing every occurrence of this fixed point formula in this proof by phi n. So basically, you can just substitute Qn, and by induction, we have Qn. And now, you can just appeal to the co-inductive hypothesis by plugging Qn omega. An important point here, is that this transformation does not necessarily give you a well-founded proof. And crucially, you need to use the progress of this proof P to ensure that this P omega construction, which we did, is well-founded. Because remember, we are going from finitely branching non-well-founded proofs to infinitely branching well-founded proofs. So we need to ensure that the object which you get at the end is well-founded. Right. So just a couple of non-examples to show you why the progress is important. A very easy example, again, mu xx. This we saw earlier is not progressing. And if we just apply our transformation here, nothing really happens, because the only thing which you do is when you see a greatest fixed point, and you never see a greatest fixed point here. So it just remains the same. So it is obviously not well-founded. In this case, you do have greatest fixed points. So our translation would do something, but it just makes things worse. Here, you have non-well-founded and infinitely branching. So it's both infinitely deep and infinitely wide. So it's very crucial that you have this really, the sort of parity condition, like even saying something like nu occurs infinitely often is not enough. Right, so we'll go to the strictness of inclusion, and this is where some of you saw the spoiler. It's not a straightforward proof. That is, we do not really exhibit a sequence that, oh, this is provable in this system and this is not provable in this system. We go through a sort of complexity argument. I find it quite cool. So a detour to via Minsky machines. I don't think I need to really introduce Minsky machines here. It's basically you have instructions like increment, decrement, and you are allowed to test for 0. So of course, the classic result is that halting of two counter machines is sigma 0, 1 complete, undecidable. This is from Minsky in the 60s. I recently learned Minsky's original paper had a mistake. Anyway, but maybe this is something which you might not be aware of. So if you impose a Bucci condition on a Minsky machine, and you ask the question, does there exist an infinite run which satisfies the Bucci condition, the complexity really shoots up into the hierarchy of like computability classes. And this is sigma 1, 1 complete from the Allure-Hensinger paper of timed like real-time systems. So right, I'll just give one reduction. This is not really the point of this paper, but it was some work which we have to do. So why not a slide about it? So let's say you want to encode incrementing A, which is like we go from a state from P to Q and we increment the register A. So this is like saying, so in linear logic, we always think of resources, right? So we consume something, we produce something. So we consume P, that we were in P, and then we produce an A, and we produce the state Q. And so let's say you were in a configuration that you were in P, you had two tokens in the register A and no tokens in the register B. And so you want to fire this incrementation. So it would look like this. You have two A's, you are in the state P, and now you are executing this incrementation. And so you do the tensor operation. It checks that you are in the right state. That's the identity, which tells you, yes, I consume this state. I am in the right state. And then it uses a disjunction to produce an extra A and give you the new state. And so that's basically one of the easy encodings. So of course, zero check and decrementation is more involved, and that's why it does not appear here. So we encode the Bushi condition using a sort of fixed point formulas. Basically, the greatest fixed points correspond to the final states, and the least fixed points correspond to the other states. And we have the reduction that if some formula is satisfiable, is provable in the normal founded system, then there is an infinite run satisfying the Bushi condition. And this gives us the sigma 1,1 hardness from the Allur-Hensinger result. Right, so why does this give us non-inclusion? Yeah, Suresh. Right, so it's like a subsystem of second order arithmetic, and you are allowed one quantification of second order.
But any number of.
Any number of first order. Yeah, it's. Right. So, come on. Yeah. So this is the idea. So we have mu-mal infinite, which is the normal founded system, is sigma 1,1 hard. This is something we proved. And now it doesn't require a lot of effort to show that a well-founded infinitely branching system is in pi 1,1. Basically, you just try everything. And that's just basically your universal quantification. And if they were the same, then you would have this because of the hardness. And now you appeal to computability theory for the contradiction. But this is apparently a non-constructive proof because I'm not really giving you a sequent. But there are some cool techniques which can constructivize this. Of course, this will give you a very artificial sequent. You won't learn anything about the systems from this, but it is still not really a constructive, non-constructive proof. Right, so since we got into complexity, we just thought, okay, what is the actual complexity of the non-well founded system? And so we were shooting for an upper bound. We were trying to match the sigma 1,1, but that didn't happen, and we didn't expect it because we think it is a bit higher. Right, so naively, it is sigma 1,3 statement because you say that there exists a proof, right? So there exists a proof such that for all branches, there exists a thread. All of these are second order quantifiers, and so that gives you the sigma 1,3 statement. But now we get an interesting bound using a proof search game. So this is also one of those techniques which might be useful somewhere else. So we build proof search games. This is pretty standard. The arena is the set of all possible sequence. The prover chooses an inference rule. The denier chooses which premise to go to. In fact, if it's this situation, by the way, the tensor situation, the prover also chooses how to branch this context. And the prover wins if the play is infinite and progressing. So the infinite play is basically a thread. It's not difficult to show that if something is provable, if and only if the prover has a winning strategy in this game, starting from this formula phi. We can appeal to
Will it still be infinite? No, suppose the phi doesn't have any fixed point quantifiers at all.
Yeah.
Then will it still be infinite?
Yeah, you're right. This is underspecified. So if if a play is finite, then it should end in an axiom. Yeah, thanks. Right. So and we appeal to analytic determinacy to get that the proof search game is determined. Interestingly, this means that our proof is outside of ZFC, in case you're interested in that. As a corollary, we get that provability is in pi1, 2. So this betters the bound of sigma 1, 3. How do we get this? It's quite simple. So something is provable is if and only if prover has a winning strategy in the proof search game. By determinacy, this means denier does not have a winning strategy, and this turns out to be a pi1, 2 statement. And so that gives us the bound. So that's the end of the story for us. In conclusion, we defined this omega system, and we compared it with its more famous cousin, the non-well-founded system. And along the way, we obtained new complexity bounds for the non-well-founded systems. And so questions which are still unanswered are what is the exact complexity? And the omega here is a bit artificial in our system, because in piano arithmetic, since you are working with natural numbers, omega is the closure ordinal. But here you might say, why stop at omega? You can go beyond. And this is something we are thinking about. Is there a natural limit? What's the intended semantics and so on? Thanks.
Thank you for the nice topic.
Questions?
So how does this compare with adding exponentials to the linear logic?
That's a very good question. So you can encode exponentials using fixed points.
Oh, nice. Okay.
So it does not increase any power.
Okay, thanks.
Okay, one question from well, any questions there? While you're still thinking, so this connection with the complexity where you said with automata, where you said that this derivability, if and only if there exists an infinite run in this Buki automaton, infinite run satisfying the Buki condition, which is like talking about the emptiness of this particular,
yes,
or emptiness of the automaton. Now, what can you say further with this connection? Emptiness of Buki automata, I suppose, is just checking for the existence of.
Right. So in this one, it was Minsky machines, but so it has been very successful, this connection. So people usually consider cyclic proofs, which are this smaller class of proofs which are non-well-founded but regular. So the set of subtrees is finite. And with regular trees, you can start deciding things, right? And you can ask something like, given a proof, given a regular proof, is it progressing? And now you can appeal to black box theorems like universality of Bucci automata or something like that, and just get upper bounds for that. And it turns out to be a p-space complete problem. And so there are deep connections. I mean, in the proof search game, which I used, if the arena was finite, you could appeal to Rabin's-Base theorem to get a regular proof, which is a really deep theorem.
Chemistry theorem.
Yeah.
One of the ways to think about linear logic is like you said, like with resources. So like the sequence are all like resources you capture and do away with. So how does so if you have an infinitely branching proof, like what does that mean for like the resources and how they stack up and how you
Right. So this is a very good question. We don't really know for the infinitely wide system. For the non-well-founded system, it's at least better understood. You can talk about co-recursive programs. Tomorrow I will be speaking about that in RHPL. So you can see like a Curry-Howard correspondence, and you can encode streams, natural numbers in just using propositional linear logic formulas with 6 points, of course, and write programs about that. So that's quite cool. Yeah, but it's not really. Yeah, it's not really informative. Yeah, we'll take this offline
Any quick questions? If there aren't any quick questions, I think it's the right time to stop.
and go for lunch.
Yeah, and go for lunch. Yeah. So I think we should thank Abhishek. Very nice talk. And nice work. And lunch now, and then we meet for the invited talk. No.
I didn't see that.